Hello, I'm Doug Montgomery, the perpetrator of your Coursera course, and I'd like to welcome you back to our March fireside chat. For those of you that are newer around here and to the whole design of experiments set of courses on Coursera, this fireside chat is something that I really enjoy doing. I run this with every month with the guest speaker, and we talk about specific topics, applications of experimental design. Some of these may be similar to things that we talk about in the course. A lot of them are sort of new ideas, new extensions of things we talk about in the course. And we always have some time at the end of the guest's presentation for some Q&A. And this is a really a terrific time for you to ask any kind of question you like. It could either be about something in the Coursera course, it could be something that relates to our guest's presentation, or there may be some question about a specific situation that you're working with that you'd like to get some advice or get our opinion on, and we encourage that. For those of you on Coursera, these fireside chat recordings get posted to the course, and you can find them in the resources tab of your course. Okay, quick reminder about how we try to run things. Please keep your microphones muted and your cameras off during the session. That avoids any extraneous noise or things like that might interrupt the presentation. If you want to submit a question to either myself or our guest, the best way to do that is to use the chat function on the Zoom menu. And you don't need to wait until the Q&A begins. You can start putting that question in anytime you want. If your question doesn't get answered during the hour that we have devoted to this, then we will try to respond to it afterwards. And you'll see that response in Coursera for those of you that are enrolled in the course. I am really pleased and honored to introduce our guest today, Annie Booth. She is a pretty new assistant professor in the Department of Statistics at NC State. Her research focuses on surrogate modeling of computer experiments involving uncertainty quantification, active learning, Bayesian optimization, reliability analysis. These are really fascinating topics. We touch on some of this in the course. We talk about some things in the course about deterministic computer experiments and space-filling designs and kriging methods for analyzing that data. But this is really fascinating stuff, and so I'm really excited about this talk. Annie completed her Ph.D. in statistics at Virginia Tech, so like me, she is a proud Hokie. And she worked with Bobby Gramercy and Dave Hidgen, and I know both of those guys well, and I'm sure that she had a lot of fun working with them. So Annie, I really appreciate your taking time to do this, and I'm looking forward to your presentation with a lot of enthusiasm.
Great. Thanks, Doug. Let me share my slides and get started. So, here we go. Thank you for the invitation, and thanks everyone for tuning in. So, like Doug said, I'm going to be talking about computer experiments and design of experiments for computer experiments, and I'll try to pinpoint throughout a couple ways that this is different than maybe traditional experimental design. But under that framework, I wanted to talk about, I think, two things that are kind of cutting edge and interesting under this umbrella of design of computer experiments. So the first one is about these deep Gaussian processes. So this is a new development that I've been working on for the past couple years, how we extend Gaussian processes to be more flexible by making them deep. So I'm going to talk about that. And I also want to bring in a cool application of design. So I'm going to be talking about a contour location type of design, but I'll touch briefly on a couple different ways that you can do design in general. So I do want to shout out my advisors, Bobby and Dave, who helped me with this research, and my collaborator, Ashwin, who is an aerospace engineer who actually brought us, very interesting real world problems. So I am now at NC State. And I do want to point out that I recently changed my name. So I was previously named Annie Sauer. I got married last year, so now I'm Annie Sauer Booth. So throughout, I have some citations and other things that will use both of these last names. So hopefully that's not too confusing. But let's get started. Where are we going to go today? Our game plan, I want to talk to you about two things. First, deep Gaussian processes as surrogate models, and then I'm going to bring in this contour location, reliability, design type of focus. And underneath each of those two sections, I'm going to follow a very basic layout. I'm going to tell you why we want these things, what they are, and how we do them. So why, what, how. That's going to be kind of our structure. So first, you may have talked a little bit about computer experiments in this course, like Doug said, but I want to motivate why we use computer experiments in general. So computer simulations are very valuable tools to either supplement or replace actual physical experiments when you can't do a direct physical experiment. So the experiment may be too expensive, it may be unethical, things like applications to epidemiology, which I've got listed in my applications below. If you want to study the spread of a disease through a population, it's just simply not ethical to try to manipulate things and see how the disease spread would change. So we simulate that. Sometimes things are just infeasible. So applications I'm going to show you later on are from kind of the aerospace background, but the first one that I'll bring in is a simulation of a satellite moving through outer space. And we're interested in the friction that the satellite experiences based on its shape and its configuration and things like that. And so naturally, we cannot just make a bunch of different satellites and throw them up into outer space and observe what happens. So we have to simulate these things. Other applications include broader engineering fields. So I'm going to focus on aerospace, but you can imagine mechanical, electrical engineering. They also have things that they want to simulate. Social networks and agent-based models are growing in popularity in terms of simulating how information spreads and things like that. I already mentioned epidemiology, and there's also, there's a long list. These are just a handful, but ecology, biology, things like how fish populations will change depending on pollution in a lake. Those are all types of things that we can simulate. So that's why we have computer experiments. They're helpful when we can't get physical data in the way that we want. Why do we now need surrogate models? So a surrogate model, and I had the word surrogate in my title. If you haven't heard it used this way before, it's just a statistical model of a computer experiment. So we also call these meta models because the computer experiment is itself a model of the real world. And now we're fitting a statistical model to the computer experiment. So there's that kind of layers of models at play. The reason we want a surrogate is that computer experiments can be really complicated naturally if you're trying to mimic the real world. Things like if you're doing an aerospace simulation, things like fluid dynamics, we know a lot about them, but they can be really complex. So sometimes these simulations are computationally expensive. You can't get an infinite amount of data. You can't run every single possible input configuration to see what happens. So you get a limited amount of training data. You can fit a model to it, and then that model, your surrogate, can give you predictions with uncertainty quantification at locations that you were not able to actually run through your computer experiment. So I have this picture up here on the right. This is a textbook that my advisor Bobby wrote, and I just want to point out that it is a really great reference if you're interested in this area. If after this talk your interest is kind of piqued or what you just want to learn more about it, this textbook is freely available online. I think it's a great resource. So that's my short little aside on that. Surrogates, though, are useful because they enable what I call downstream tasks. This is where the design component comes in. Things like Bayesian optimization. If you want to try to find the input configuration that gives you the maximum output from your simulator. Maybe you want to find the design that's most efficient or the cheapest to build or experiences the least amount of risk, things like that. You can also do things like calibration. That's what we call when we're have some tuning parameters of our computer simulation, and we may want to calibrate them with a little bit of real world data to try to make our computer simulation more applicable to the real world, because it's always simplified in some sense. You could do sensitivity analysis on your inputs, all of these enabled by your surrogate model. And lastly, I'm going to talk about this contour location at the end of my talk, which falls into active learning. We also call this sequential design. This is the process of strategically collecting your data. So this is where the design of the experiment comes in, using the surrogate to inform which inputs you should collect or you should run through your simulation next. And all of these things are just more important if your computer experiment is expensive and your data is limited, so you need to be more strategic with your design. So before we revisit that later in the talk, I want to motivate why we may want to use deep Gaussian processes by telling you some background on regular Gaussian processes. So why may we want something deep? Well, because the thing that is not deep is sometimes not that effective. So if you've heard the term Gaussian process before, you probably have heard it as referring to a multivariate normal distribution type of model. So a Gaussian process is simply a prior distribution that follows a multivariate normal PDF. So these GPs, we like them for computer experiments because they allow you to fit things that are nonlinear. They're non-parametric, so as opposed to a typical linear regression model where you can only fit linear or polynomial, you're basically doing things linearly with a beta kind of slope parameter. The Gaussian process does things non-parametrically. It's more flexible to fit the type of surfaces that we have in computer experiments, which are usually nonlinear, and it also comes with really great closed form uncertainty quantification. So as a basic assumption, we just say, okay, multivariate normal distribution over our response. I'm going to use a zero mean without loss of generality just to keep things simple. And then all of the work in our model is in this covariance function sigma. So this function accepts inputs like two locations, xi and xj. It looks at the Euclidean distance between those points, and then it does some kind of function of that to tell you how correlated the response is at those locations. So you can imagine points that are closer together, the responses of those points should be more correlated than points that are further apart. So that's all encapsulated in this covariance. I've highlighted in blue some common hyperparameters that we usually build into this kernel. This tau squared is like a scale parameter. This theta is like a length scale, which is going to control how fast that correlation decays or how close needs to be close, relatively speaking. And this G is what we call a nugget. It allows you to model noisy data. For the rest of this talk, we're going to deal with deterministic computer experiments. Although there exist noisy computer experiments, we're going to deal with just deterministic ones for now on. So assume that we fix this G to a small number. Now, in the plot on the right, what am I showing you? I am showing you a hypothetical set of data that we got from a black box computer experiment. So it's just one dimensional. I put in these X locations and I got back out these Y locations. So each red dot is representing a run from our hypothetical computer experiment. And we want our surrogate model to be able to predict this whole surface at specifically points that we have not yet observed. So why is a Gaussian process helpful? As a prior, we're not really getting much information from it, but when we take that prior and we condition on data and we get a posterior distribution, now we are in business. So if you go to the Wikipedia page for, multivariate normal distribution the conditional distribution, you can find these closed form moments really easily. These have been derived in textbooks going back decades, that if you have something that's normally distributed and you condition on something else that's normally distributed, your posterior is also going to be normal, and it's going to have these moments, this mu star and sigma star, that are simply functions of the covariance and the data that you observed. So what does this look like in a figure? Well, the plot on the right is now showing you the predicted value in the dashed line. That's the predicted mean. And then the confidence intervals are shown by the shaded region of a regular GP. So all I did was I conditioned on the red data points and I calculated this mean and variance, and I used that to make this plot. I will say that those hyperparameters I mentioned on the last slide, We usually have to estimate them from data, so we usually will do something like maximum likelihood estimation or MCMC sampling. Those are both common choices. So what do you think about this fit, though? Given these red data points, and given the fact that we know this is a deterministic computer simulation, is this a good fit to this data? Well, we could go back and forth on this. It looks like it's doing a pretty good job of getting the nonlinearity on the left side of the space, but it looks like it's suffering on the right side by overinflating the variance, right? So we can see pretty clearly there's a linear trend on the right side of this data, and yet the variance kind of football shapes in this graph are really big there, where we should be a little bit more confident as compared to the left-hand side. So what's happening here? This is a manifestation of stationarity. So I'm plotting now in the black dashed line, the true function where I pulled these red data points from. I came up with this function myself. It's just a piecewise function. This is the fit that I showed you, and I just want to introduce the terminology that the reason this GP fit is not ideal is that it is handicapped by stationarity. So that means that it cannot incorporate information in the predictions that, aside from that squared Euclidean distance that's going into the covariance kernel. So we're basically, all of our predictions are based on the relative distance between inputs. Not necessarily that's not something that can enable you to identify like, oh, this region is different from this region. There's two separate regimes. There's a stark transition. So that stationarity is handicapping us. It's not flexible enough to model this complicated surface. So as a preview, this is what our deep Gaussian process can look like on this data. There are other approaches to modeling non-stationary functions with Gaussian processes. One of the things you can do is change your kernel, make it more complicated. That is common in spatial statistics. So my advisor, Dave Higdon, actually had this paper back in the 90s doing just that very thing, make your kernel a function of more than just Euclidean distance. The problem with that is that it doesn't generalize well to higher dimensions, which is why people in spatial stats with 2 or 3 dimensions were pretty satisfied with those types of methods. But in our computer experiments, we often have like 7, 10, kind of moderate amount of input dimensions. Another thing you could do is you could partition the space and fit a treed Gaussian process, or you could do something local. So imagine with this function, we cut the space where we can clearly see that the piecewise shift is occurring around 0.6 on the x's. We could fit a separate Gaussian process on the left side and one on the right side. The difficulty with that is that you have to figure out where to cut your input space, where to partition it, and that's really hard to do in higher dimensions when you can't just eyeball it. And you also have now these 2 separate GPs on the different partitions, and they're not speaking to each other. So we wanted a surrogate model that can be flexible enough that it can model non-stationary surfaces, but it can also maintain globality all at the same time. It can help us do really easy global inferences. Really easy. It's a little complicated, but it works out to be nice in the end. So that's why we are bringing in deep Gaussian processes. They actually originated in spatial statistics decades ago, and they recently became popular in machine learning communities. And now we're bringing them into surrogate modeling. So what is a deep Gaussian process? It is just a functional composition of regular Gaussian processes. So if you direct your attention to this left panel of this figure, I'm showing you a nice smooth function that I just drew from a GP prior, x to y1, it's nice and smooth, and the color gradient on the bottom is showing you just that I started with an x that was uniformly spaced out. Now I take that y1 and I feed it in as an input to another Gaussian process to get y2. So that's in this small panel shown here. Those 2 functions are just simple Gaussian processes. The building blocks are things that we already know. But if we look now from x to y2, so we skip over y1, and that's what I'm showing you in this middle panel. This is now a 2-layer deep Gaussian process because it was the composition of 2. And the color gradient on the bottom is trying to convey the distribution of y1, which is otherwise left out of this middle panel plot. It's showing you that y1 is actually stretched out in the middle and compressed on the edges. So it's like a warped version of x, where this steeper slope in the middle effectively stretched out my inputs there, And then the shallower slopes on the edges effectively squished my input. So think of this as just a warping. And then I have the other panels here just to show you that you can add on other layers and go deeper and deeper. But for our purposes and for all the computer experiments that I have investigated, 2 layers has been enough without getting too complicated. So we want to be as parsimonious as we can while getting the flexibility that we want. So moving forward, we're just going to talk about 2 layers. Okay, a little more concretely, let's switch, since we're only talking about 2 layers, instead of calling it x, y1, and y2, let's call that middle variable w. And I'm calling it w because I want you to think of it as a warping. So imagine that we observe inputs x, those go into a Gaussian process to get w, and w is effectively a warped version of x, and then that w goes into a Gaussian process to get to y. So that's our 2-layer model. The W, I've got a subscript here, K, just to represent that it can have multiple dimensions. So imagine your X design matrix is some N by D matrix. You probably want your warping to also have D columns to match the dimension of the inputs. So that's just what I'm referring to with these kind of separate nodes. Each column of your W is a conditionally independent GP. But altogether, they go in as a warped version of your inputs into the outer GP for Y. The tricky part here is that what we really want to do is statistical inference on this likelihood of Y given X, but that requires integrating out this unknown variable W from this joint likelihood. This integral is not tractable in general. We can't just integrate out this unknown quantity when we're putting together these 2 GP components. So what do? Well, we can approximate the thing that we can't directly integrate. We call that approximate variational inference, and I've just noted a couple citations here just to drive home the point that this is very popular, specifically in machine learning, where people are trying to use deep GPs to do things like image classification, and they have a whole bunch of noisy data. We instead are going to do MCMC sampling of the unknown quantities. And we're going to do the sampling so that instead of approximating the integral we don't know, we sample through the whole posterior distribution of unknown quantities. That gives us better UQ. So the MCMC that we do, I want to point out that the key part of this is how do you sample W, which is functional. It's just like a Gaussian process, so it's functional, it's got multiple dimensions potentially, and we do elliptical slice sampling of the latent W. We do Metropolis Hastings for other hyperparameters. You can do different things with that. You can do some kind of MLE equivalent. Those covariance hyperparameters are not super important. What is important is getting good estimates of your warping, W. So I've got this diagram here, which just shows you a preview of what elliptical slice sampling looks like. And I want to direct your attention to just 3 points. The first point is that you start with a sample from a Gaussian process prior. That's easy. Just draw a line, just like that plot I showed you of what is a deep GP. Every single line in one of those plots was just a random draw from a prior. Then this proposal box, our proposal is just a weighted average of our last sample and our prior draw. So instead of, proposing little bitty changes to this function, we're proposing a whole new function all at once every time. That gives us better mixing in the end. And then we're accepting just based on the likelihood ratio, which is pretty standard. Then if our likelihood ratio does not give us an acceptance, we don't start over, we don't quit. We simply adjust our weighted average to put less weight on the prior and more weight on our previous sample. And then we keep adjusting until we get an acceptance. So this is free of tuning parameters. It gives us great mixing, but it does only work if you have a Gaussian process, which we do. Okay, quick aside note on software. I have wrapped all of these things in the DeepGP package on CRAN, so I encourage you to check that out if you're interested. If you had training data X and Y, which would be these red points, you can plug them into this fit 2-layer. Then you can trim your MCMC samples by cutting off burden and maybe thinning some of the samples you have left, and then you can get predictions. So that's how I generated this predictive plot down here on the lower left. On the right plot, I'm now showing you each gray line here is a sample of that latent warping for this space. So each gray line has a positive or negative slope. Doesn't matter the direction of the slope, but it has a slope at the beginning, which is effectively stretching the inputs. And then it squishes at the end or flattens out at the end to compress the inputs. So the warping is stretching out the interesting region where all the signal is, and then it's squishing the linear region where there's not that much going on. And that's how we get this more flexible fit. So in 2 dimensions, I have an example here of this G function. This is what the surface looks like on the left. The warping is harder to visualize, but I'm showing you in the middle panels here just one sample of 2 nodes of W, because in 2 dimensions, we want to have 2 dimensions of W as well to kind of match the shape of our design matrix. And when you look at those together, the right panel here is showing you how they are effectively warping the inputs kind of by pulling it in the diagonal directions. And that's what gets us better predictions. So I have some plots here of just predictive results for that same function bumped up into 4 dimensions just to convince you that the warping does give us better predictions. So the green here is our deep Gaussian process compared to orange, which is a regular Gaussian process. And we are getting better root mean squared error and also better scores, which is this CRPS on the right, which just means we're doing better at predicting with the mean and getting good UQ. But let's go to a quick real world example. I don't have any pretty pictures of what the simulation looks like, but we have a simulation. It's called the TPM simulator. It was developed by folks at Los Alamos a couple years back. It simulates a satellite moving through outer space. So we have 7 dimensions representing our X that define the satellite configuration and some aspects of how it's moving. And our response is the friction that the satellite experiences as it goes through outer space. They call it drag. Our goal was to get predictions with as little training data as possible and get a prediction error below 1%. So I'm showing you now, red is our deep Gaussian process, yellow is our typical GP, the same metrics, prediction error on the left, score on the right, and even across these different training data sizes, we are able to get better predictions. So that's the end of my deep Gaussian process talk. I think hopefully it's interesting to see how we can take these typical Gaussian processes and put them together to get more flexible models kind of on the cutting edge of current research. Now I want to transition to talking about a specific design piece motivated by another real-world aerospace example. So our motivation for this design piece of this latter portion of this talk is that we have a separate computer simulation. It also has 7-dimensional inputs. Some of those inputs are defining the shape of a wing of an aircraft. Some of those inputs are the angle that we're flying at and the speed that we're flying at, but the simulation takes an aircraft wing and models how it moves through the air using fluid dynamics and complicated stuff that I don't know. And the engineers are very smart on this stuff, but I imagine this is a black box. We put in some configurations about the wing of our aircraft, and we simulate how it moves through the air, and then we look at this output variable, which is the lift over drag ratio. Lift and drag are like concepts of flight dynamics, but you can think of this as simply an efficiency metric. Based on the design of the wing and how it's moving, how efficient is our flight? And we want our efficiency to be good. We don't want bad efficiency, then we are using too much fuel, it's bad for the environment, all kinds of downstream ramifications. So our goal here was that we wanted to identify the inputs of the values of these 7 inputs that when they go through this simulation, they give us passable efficiencies. So in our response, imagine that we have a threshold, we're using the quantity 3, and we're going to separate values below 3 are not efficient enough. We call those failures, and values above 3 are efficient enough that those are passes. So our whole goal, our downstream task, is to find the inputs that create this contour between passes and failures. So what did we do? Well, we started with a Latin hypercube space-filling design, like Doug mentioned at the beginning, of 500 points spread out in these 7 dimensions, and we looked at how our models performed on a holdout testing set. Now I'm showing you in green our deep Gaussian process with the elliptical slice sampling. Blue is a typical stationary Gaussian process, and just for fun, this yellow is a different way of doing a deep Gaussian process using variational inference. So I used the PyTorch package in Python to fit this yellow one. It is not doing well. So that's just an additional comparator, but it is not our focus. Our focus is on the green and the blue. We get better RMSEs, we get better scores, lower is better on the two left. Specifically, though, if our goal is to identify this contour between passes and failures, we may want to look at our sensitivity and specificity in predicting those failures. So those are shown on the right two panels, and higher is better on that. We want more sensitivity, more specificity. So far, this is just a space-filling design. There's nothing interesting with the design that we did here. We just spread out some points. We can do better if we do something strategic. So this diagram I'm showing you here is just a general idea for active learning sequential design. We start with a small design, we fit our surrogate, we select our next input to run through our model based on information from our surrogate. Then we run our model and we update in this feedback loop. You can do things like Bayesian optimization with this. You can do all kinds of different research objectives or downstream tasks. We're going to focus on just the one of finding a contour. Once you have a contour or a surrogate that can identify passes and failures, you can do reliability analysis. So that's an extension of this work to actually figure out what designs of my aircraft wing or my satellite or my automatic vehicle, all kinds of interesting applications for this work. You may want to find out which ones are safe enough. So that is an extension that we're not going to talk about today. We're going to talk about training our surrogate to find the contour. So here's a quick example of a two-dimensional function. I call it the plateau function. The heat map on the left is just showing you the surface on the right in a different way. So white is high, red is low. Imagine this was our surface from our computer experiment, but we only got to observe some limited training data from this surface, and we wanted to predict the contour, which is the blue line. So in this case, the blue line is our failure contour. Failures are in the white region, and passes are in the red region. So I fit a deep Gaussian process to some random training data. So now these black points are random training data. We observe the function at those points, and the heat map here on the left is now showing you the prediction from my surrogate. The white is the high region, red is low, and the black dashed line is showing you where my surrogate thinks the predicted contour is. It's not terrible, but it's not a perfect match to the blue line. So in the middle panel, I'm showing you the standard deviation that goes along with that, and you'll notice the standard deviation is high in the yellow regions where we don't have a lot of data. It's a little bit higher around our predicted contour, and it's lower where we observed data. So together, that's our mean and variance from our model. Now I'm showing you entropy in the right panel, which is the most common acquisition criteria if you want to find the contour. So we could say, let's put our next point at the location where we have the highest entropy. If you don't recall entropy from any of your previous classes, it's a measure of your pass-fail uncertainty. So entropy is highest where your prediction for passing and failing is 50-50. It's really low if your prediction is 100% it's a failure or 100% it's a pass. So it's maximized around that 50-50, which is why our entropy surface is maximized exactly where our predicted contour is. So if we wanted to do our sequential design, we could put a point where there's highest entropy, run the model at that point, update, and keep going. We could use that. That's what has been done in the past. We have some more recent developments, which we think do better, and we have some evidence they do better. Our strategy is actually threefold, and I don't have time to get into the details of this, but I just want to point out what we do first is we strategically propose some candidates in the space. We call them triangulation candidates. So the red diamonds in this left panel are going to be where I'm proposing my candidates. I'm going to evaluate entropy at all of those locations, but I'm also going to evaluate predictive standard deviation at those locations. So now in the middle panel, the purple points are where my candidates are, where I've evaluated their entropy. And then I'm actually going to choose not the point with just the highest entropy, but I'm going to choose the point that has the highest entropy and the highest uncertainty. So that's where we call the Pareto front of entropy and uncertainty. So I'm actually going to end up choosing one of these purple triangles instead of one of these purple circles. So key takeaways are be strategic with how you're doing your sequential design, but when you combine a deep Gaussian process with the strategic design, we can really learn where a contour is. So I have some results for that function, plateau function, but now in 5 dimensions, which is much harder than 2 dimensions. And we were looking at start with a small LHS. So we started with 20 points as an LHS in this 5-dimensional space. And then we did the sequential design of choosing the candidate with the highest entropy and uncertainty update, and then repeat this process. So the left panel here, I'm showing you the sensitivity at how well we were predicting failures across our whole sequential design. And the deep Gaussian process can significantly outperform a regular Gaussian process, and even a regular Gaussian process that's using the exact same sequential design. So the orange is the exact same sequential design, but not deep. And the blue is what we considered the state-of-the-art Gaussian process that is just using entropy. Now, on the right panel, I'm showing you how the results at the end, after we had 150 points, so we did 20 to start, and then we collected 130 points at the end, we did a couple Monte Carlo repetitions, and we looked at the sensitivity for those 3 different metrics. We compared that to what you would get if you just did a static Latin hypercube of the same size. So these left 3 box plots are all sequentially designed for contour location, and the right 3 are all just regular Latin hypercubes. And if you compare the green and the green, that's showing the effect of the sequential design, because otherwise the model is exactly the same between the 2 green box plots. So almost all the models significantly benefited from this contour locating sequential design. And if we return to our motivation, I showed you these green and blue box plots before. This was our 7-dimensional simulation of this aircraft wing. And I showed you the sensitivity and specificity of the deep GP and the regular GP. Now I'm showing you in the left panels with these lines, the sensitivities and specificities we get if we do a sequential design instead of just a space-filling LHS, and we're able to achieve better sensitivities with a lot less data when we design them strategically. So I think I'm out of time. That's what I wanted to talk about today. Everything that you saw is supported through this deep GPR package. And I also have a Git repository with all kinds of examples, so you could recreate everything from this presentation today. I hope I gave you a little bit of an overview of some interesting cutting edge developments in this area of design of computer experiments. We do have hopefully time for questions like Doug said, but if you encounter questions later on, I am reachable through my email pretty easily, and I appreciate you all tuning in.
Annie, thank you. Thank you very much. This is really fascinating material. I think these are some really significant advances in computer experiments. It just tells me the next time I revise my experimental design book, I have to think harder about what.
Yeah, we're working all the time, you know.
Well, I'm really fascinated by this whole business of computer experiments, and before we get to questions, I'll tell you one interesting thing. You mentioned simulation experiments to study problems in epidemiology. When I was at Georgia Tech, I was a faculty member there for 15 years, and I had some connections with people over at CDC, and some guys from CDC approached me, and they said, "We're trying to figure out how to model the spread of rubella, you know, a form of measles." And because in that era, measles was a really big problem, and had less so today because of more effective vaccinations. But I had a master's student that we actually developed a computer simulation model that did a very good job of describing how the rubella epidemic spread. And we validated it against data that they had collected on 2 or 3 different large-scale epidemics. And it was really quite an interesting project. It was actually rather fascinating, and we somewhere in the depths of my resume there is a paper that we actually wrote on this that got published in a medical journal somewhere. And the CDC, the CDC people were really quite excited about this, and they were going to go off and do some other work with trying to develop computer models of epidemic processes. And I just never kept my foot in that particular door, and so I don't know how much it actually worked out. But are you aware of people actually doing that sort of thing?
Yes.
Oh,
So the work with computer simulations is super collaborative because you really need a combination of the experts in
sure.
the area who can, understand the dynamics to build into the model with people like us who do, modeling and the design of the experiments. And so I have not worked myself with any like health area experts who
Hmm.
have done these simulations, but I know that they are out there, especially for example, like I think when COVID came out and they were doing a whole lot of simulations of the spread of COVID and how much distancing will help. And that a lot of that was based on simulations of the spread.
Hmm.
Like, will masks help? Will distancing help? But there's a whole class of models for that. And of course, the models were, newer and not as developed. And so, you have to develop the fidelity of your model at the same time that you're developing the methods for modeling it. So um, less developed, but very collaborative and growing in a lot of areas.
I'm really kind of pleased to hear that, because we worked with MDs over at CDC, and after the student finished her master's degree, she ended up taking a job with the Tulane University Medical School as a biostatistician. And I'm not, as I said, I've kind of lost track of all of that because I've moved on to other stuff, but I was always kind of fascinated by it, because we did have a fair degree of success in the CDC people were thrilled, and it was fascinating.
Yeah, I mean, there's a lot of this is spurred by, as we understand more about the science behind things, we can model them more effectively. So,
Right,
in general, just growing scientific knowledge is growing the impact of these computer models,
right.
but it's also related to computational advancements, right? So, the more access we have to high performance computing, the more we can actually simulate these things that we didn't have the capability to do in the past. So, I mean, it's everywhere. Health applications, even economics.
Hmm.
They do a whole lot of simulations in that realm. And like I said, my primary collaborators have all been engineers. So that's where I've been doing most of my work on those kind of physical sciences applications, but it's certainly broad.
I've seen that actually through my course here on experimental design. I teach an introductory master's level course on design of experiments, and I get a lot of students in it. Between the campus and online students, I probably have 100 students in a typical semester. So it's quite a crowd. And I make them all do a project where they actually have to design an experiment, run the experiment, analyze the data, and write up an intelligent report. And
That's the
I
hard part usually.
Yeah, well, I have them do the report in three phases. They do a proposal. They tell me what they want to do, and then they have to come back with an actual experimental design. I'm in the process of reviewing all those reports right now, and then they have to actually conduct the experiment and write up the results. Well, what I've seen, which is fascinating, is the number of these students that are using computer models in these projects. It's
Oh, really?
growing dramatically.
That's cool.
It was, if I go back, and I've been teaching this course here for, well, I'm aging myself. I've been here for 35 years. Okay. And I've been teaching this course a couple of times a year for a lot of that period of time. And I've seen these computer models, the use of them going from zero to where now that maybe as many as 10% of these project teams are using computer models in their project experiment. You know, and they're from all fields. They're computational fluid dynamics type things. They're stress strain type stuff, you know, finite element model type stuff. There's all kinds of things, and I'm just
Mhm.
fascinated to see how this is growing. And you know, like I say, I'm finding myself having to talk about these computer experiments earlier in the course now, to make sure that they know enough to be able to do this. And I just want, do you teach a basic design course at NC
I
State?
do not yet. I am brand new. This is my first year as a
Yeah.
faculty member. So I got the easy out this year teaching an introductory course so that it wouldn't be too much of a workload.
Right.
But I am hoping to teach a surrogate modeling graduate level course
Okay.
soon. The I don't know if it will ever really infiltrate into the undergraduate level
Yeah.
courses, although maybe it should. I think it's really interesting.
Well, my course is a graduate level course. It's a 500 level course, but it does require that they have a prior course in statistics. And
Yeah,
so
good.
they come into the course knowing, hopefully knowing something. Uh, it, it,
I,
it depends how good their undergraduate course was.
hmm, I
As
do
you know,
think it's
not all of
interesting.
those undergraduate courses are great courses, you know.
Yeah.
So,
I
but
do think that one of the interesting things now that not too many people are thinking about is we talk about how in some cases doing a real experiment is unethical.
yeah,
And so computer experiments can help in that situation because you can simulate things like epidemiology and stuff. I think well, the conversation over the next, you know, span should maybe focus on the ethicality of using these computer simulations to actually make real decisions without taking into account, you know, the fact that they're not the real world. I
right.
think that's like a really relevant area is how do we almost like calibrate? Calibration is, I think, getting to this point. How do we calibrate our decisions based on the fact that the computer simulations are never like the real world? So I
That
think that's
that
something not enough people are talking about.
that is a very good point, and you know, I, I agree with you. And by the way, if you start thinking about teaching this graduate course, uh, let me know what's going on, okay? Because
Okay.
I'd like to see what you're doing in that course, and maybe I can steal some of your ideas and incorporate them
Yeah,
in my course.
I will say I'm going to borrow heavily from Bobby's course that he taught that I took as a student
Okay.
um, on computer experiments. Of course, you know, not I'll put in, you know, some newer things because that course has been in development for a while. And this area is growing all the time.
Yeah, it certainly is.
But yeah, Bobby's textbook is a awesome resource. He's got homework problems and stuff in there too.
Yeah, I've seen it, but I've not dived into it in any great detail, and I probably should because I think it is probably the authoritative reference on computer experiments.
Yeah, right now, maybe. Yeah.
Yeah,
I would think you're right. I think there's a lot of different people working in this area. But I think that's one of the more accessible to a newer kind of graduate student
hmm
population
hmm
who are not experts in the area. Yeah.
Well, let me before we get to questions, let me recount one other experience with computer experiments. I actually had a PhD student whose dissertation work was in computer experiments, and she worked on a really particularly interesting problem. This was a research project that I had with NASA and out at NASA Langley. And do you know Peter Parker from NASA?
I do. Yes,
Okay,
I worked for NASA Langley 2 semesters
okay. Well,
actually when I was a grad student. It was
Peter
very
was
cool.
Pete was the guy that sort of motivated this whole thing, and that's how we got this research project. And we were working with a group of people that were trying to develop a new type of propulsion engine, okay, that is going to make getting to Mars a lot simpler, okay. the problem with conventional rocket engines is once you shoot this thing up into space and you hit escape velocity, you're not going any faster. Okay, you know, and you're gonna travel at that rate of speed until you get to wherever you're going, which could take months and months and months if you go into Mars. So the idea was this engine was going to be able to continuously fire. It was called an ion impulse type engine, and it was going to be able to continuously fire so that you would constantly accelerate. So maybe not very fast. Maybe you'd only gain 1 or 2 kilometers per hour, every day, but that makes a big difference in terms of how long it takes you to get somewhere. And so the physics behind this thing were really quite complicated. And the guys that we were working with ended up building this very complex computer model that basically explained how it worked. Okay. And our piece of this project was to help guide them through the experimental design work. And it turns out that this model, it was not completely a deterministic model. It was, we called it a model with low noise. Okay, if you ran the same set of conditions twice, you got almost exactly the same answer. Okay,
I've seen some like that.
There are some obscure reasons as to why this happens. Okay, but in her dissertation, she ended up developing a type of experimental design for a computer model like this that worked extremely well. And we worked with some with Brad Jones too at Jump.
At Jump, wow.
And we call these things bridge designs. And because they are a bridge between, the classic, factorial type design and a traditional space filling design. And they worked extremely well. And we actually have a couple of papers that talk about bridge designs somewhere. I always forget. And she went on into the academic world for a while, but then ultimately bailed out and went to industry because they offered her too much money. So so she got out of the research business, but it was a fascinating project, and they were just about getting ready to build a prototype for this thing and haul it up to the space station and test it out. Okay, and then
wow.
In their infinite wisdom, Congress decided that we weren't going to Mars. And so the funding for this whole thing disappeared. And nothing has ever happened with this since then. And
Wow.
well, it was fascinating. I got some real insight into the way people really utilize a lot of these computer models. And of course, having her go out there and spend time with people from NASA was really enjoyable for her. And so it was a great experience for a PhD student. And I'm sure you enjoyed your time at NASA.
I did. Yeah, NASA has all of the interesting simulations.
You bet.
The one that I worked on when I was there, I spent most of my time on was a simulation of they're building a new spacesuit. And apparently it's very common for astronauts to fall over when they're on the moon and hit like a moon. Right. So the simulation was the new spacesuit like falling and colliding with a rock. And we had to make sure that it did not fracture.
Yeah, that would be bad.
Yeah, so they simulate a lot of stuff at NASA for sure.
Yeah, I have done a little bit of work with people over at JPL in Pasadena, and same thing. They do a lot of computer modeling of things as well. Well, let's see. We do have a question that has popped up on the screen here in front of me.
Cool.
And I'm not so sure it's a question, but it's a comment. It says, I seldom, if ever, see linear regression techniques discussed when analyzing experiments, but there are settings, particularly or especially in online experiments, where continuous covariates are collected and where I found it useful to control for such covariates by including them and possible interaction terms in a linear regression model. Yeah, this is called analysis of covariance. And it's a pretty standard technique. In fact, if the person that wrote this question reads my experimental design book, they will find material in there on analysis of covariance. And in fact, it's discussed. It says, does this make sense, or why does it look like linear regression isn't more discussed in books on experimental design? All I can say is read my experimental design book. Okay, because I have a whole chapter on linear regression, and then there's a whole big section in another chapter on analysis of covariance. And I always talk about it in my class because it is a very common problem. You know, and the example that I use to motivate my students is, suppose you're developing a new type of cattle feed, okay, and you want to see, you know, does the new cattle feed produce more weight gain, you know, than the old cattle feed? Okay, so simple experiment, you know, one factor, two levels, okay, old feed, new feed, and the response variable is how much weight did the animal gain? Well, do you think the amount of weight that they gained is related in some way to the initial weight of the animal? Probably, right? So there's your covariate, right? And I have a pretty comprehensive example of this kind of thing in a real experiment. It's in the book. So yeah, it makes perfectly good sense. It's a standard technique, and you should definitely think about doing this because it can add a lot of insight.
I will add in the Gaussian process models, what a lot of people do if they have something like that is they change the mean. So in my talk, I said just use mean of 0 and it
Yeah,
simplifies everything and it's fine. But you can make the mean actually like an X beta, where your covariates are built into the X, and then you can estimate the slope parameters that go with them. So I think you could build that into a Gaussian process model.
I think you can. I think I've seen that done.
Mhm.
And it seems to be a logical thing to do. So yeah, this question is very good, and it does make sense. And
Yeah, oftentimes the tricky part with these simulations is sometimes figuring out what all your inputs should be. I mean, if you say you have an airplane wing, it's like a physical 3D object. How do you actually parameterize that in a couple of inputs?
right,
And that's a whole different monster, I guess. And so that goes into it. Like, what actually are you going to make your inputs? What are your knobs for your simulation?
right,
And oftentimes we figure that out by, working with the experts in the area.
yeah, and airfoils are particularly interesting because they are complex geometry. And we know what we want as an output. You know, that lift drag ratio is really crucial. But there are a lot of other parameters that you can vary. I did some work with Ray Hill from AFIT. I don't know if you've ever encountered Ray or not. He's a
Not yet.
professor up there. Well, he just retired, but
Oh, okay.
but he was a professor up there for many years and taught a lot of their experimental design work. And we worked with some people at one of the Air Force test sites where they do wind tunnel work, and we looked at ways that they were running experiments in their wind tunnel on different airfoils, and found some ways to parameterize those experiments in efficient ways to make it less painful to actually do the wind tunnel, because wind tunnel testing is really very time consuming and pretty expensive. And we found some ways that they could improve that, but these are physical experiments, not computer experiments. But I can see where parameterizing some of those airfoils for a computer experiment would be very complicated.
Yep.
It would be very complicated.
Yeah, it definitely is. And often it comes down to things like how dense do you make your mesh
Yeah.
of the
Yeah.
wing type.
Well, that's the typical finite element type problem, you know,
Yep.
how
How dense?
yeah, how do you do that? I'm getting the time to sign off signal from our director here, so I'd better stop. Annie, thank you so much for doing this. Is a fascinating talk, and it's a fascinating area that
Thank you. I
I should
appreciate the invite.
I should really do more of this in the course because it is a growing area. This is one of the real growth areas in experimental design work. And let me know when you start thinking about teaching that course because I'd like to collaborate with you on that.
Yeah, will do. That sounds great. Thanks for everyone for the invitation. It was a great experience.
Lovely to have you. Thanks a lot. Go Hokies.
Go Hokies. Yeah, that's right. Women's tournament. Here we go.
Here we go. Bye-bye.